Welcome to the Picture Language Seminar. Today, we're very pleased to have Jeongwan Haah. He's going to tell us about topological phases of discrete time evolution. Jeongwan was a student in Seoul at the National University, graduate student of John Preskill at Caltech, spent 3 years, 2013 to 16 at MIT, and then joined Microsoft, where he's one of the young stars in quantum information. We've heard about the Haah codes, which are related to fracton models, but today we're going to hear about something new. So Jeongwan, why don't you share your screen?
Okay, thank you. Yeah. So I am going to tell you about a new object on the time dynamics, although most of my talk will be focusing on a static object. Later we will have some time to discuss why I chose the title as it is. So let me begin with a review of quantum circuits. You may have heard of the quantum circuits many times, but let me just repeat it for you. Suppose we have a one-dimensional chain of spins for each lattice point on this one-dimensional line, and there is some quantum two-qubit unitary that acts on the pair nearest neighbor qubits, and it can act on in a fashion like that goes like this, where the vertical direction refers to the application time. And if we have such a short, small depth circuit, say depth of t, and then if we consider the action of this quantum circuit as the conjugation on some operator that is sitting here, then we can calculate the effect of the quantum circuit in this way. I am drawing the dagger of the blue unitary below, like that. This is an exact mirror image about this middle black line. And by unitarity, and since we are talking about this part is U and this part is U dagger, so we can cancel off that is not blocked by operator X. So I am calculating U times X times U dagger, and cancellation will go like that. So what I'm left with is just a light cone by which the X is now conjugated. So the lesson from this calculation is that the support of this conjugated operator is contained in the some small neighborhood determined by the depth t of the support of the original operator X. So the important thing is that for small depth quantum circuits, the locality is preserved. And this is quantitatively equivalent up to some small factors that are not important conceptually to the well-known Lie-Robinson bounds. If you evolve an operator X in the Heisenberg picture by a Hamiltonian H for some small time t, and if you take the commutator of arbitrary operator Y, then the operator norm of that commutator is some factor that depends on X and Y only, and there's an exponentially small suppression between that determined by distance and evolution time, where this mu and v are properties of the Hamiltonian only. So in many regard, the quantum circuit captures the property of this continuous time evolution. Where do we use this? In the study of topological phase of matter, the primary use of quantum circuit relies on this fact. If you suppose we have some Hamiltonian path, the lambda is an abstract parameter that parameterizes my one parameter family of Hamiltonians. And suppose I have a gapped Hamiltonian that starts at here, and suppose the first excited state has an energy that varies like that. The important thing is we are here assuming that the energy gap above the ground state is lower bounded by some positive constant. In this case, the ground state at lambda equals 1 at the end of my Hamiltonian path is related to the original ground state at lambda equals 0 by some unitary conjugation. And this unitary is also a comes with the one parameter family where the intermediate unitary satisfies differential equation that looks like just Hamiltonian evolution, where D is sum of local terms, yeah, of course, Hermitian. So
ordinarily that would be Hamiltonian.
Yeah, I can call it Hamiltonian, but this dt is not exactly the Hamiltonian that I'm considering in this Hamiltonian path. It is some variant of it. So since ground states are the primary focus in the study of topological phase of matter, these unitary are represented by some small time Hamiltonian evolution, and the picture of quantum circuits enter to understand conveniently to understand this unitary. And that's the connection between small time evolution and the topological phase of matter. So colloquially speaking, I am putting the statement in the quotation mark. The topological phase of the definition is equivalence classes of states to small depth quantum circuits. This is almost precise, but only almost, not exact. So I put the statement in quotation marks. Okay, so that was a review for the quantum circuits. And let me change my gear a little bit to talk about Walker-Wang models. Here, Wang is in the audience, Jeongwan. This is a lattice model of the historically prior Crane-Yetter TQFT. This is a machinery where the input is some algebraic data of 2 plus 1 dimensional Kenyan theory. If you give me such an algebraic data, then this machinery provided in the Walker-Wang model, although model refers to one, it is actually a schema. It produces commuting Hamiltonian on some special class of, very general class of 3-dimensional manifold, whose ground state is a superposition of physical meaning, superposition of configurations of its physical meaning. It comes with a vacuum component. It comes with some certain string configuration, which may be knotted or twisted like this. And there are many, many components. Here, the amplitude is precisely the quantum amplitude of the process when you interpret each configuration as a Annian word line, and this amplitude is proportional to the the amplitude of that quantum process. The particular 2+1D annual theory that I would like to discuss is so-called three fermion theory. It has four simple objects, including the vacuum, denoted as ABC. They are all fermions, so their topological spins are always -1. And the S matrix that describes the mutual grading is like this. So distinct fermions mutually braid to give -1, and all the other combinations give +1. And consequently, from this topological spin, the higher central charge determined by this anyon data satisfies -1. So in particular, the higher central charge C- is never 0. So if you have some two-dimensional medium that has a spatial boundary, then at the spatial edge, there is a chiral edge mode. This data doesn't tell you where that edge mode goes. It can be right or left, but it's anyway non-zero. And that is the only thing I made. It comes with the produced three-dimensional commuting Hamiltonian satisfies a number of properties. The first thing is that its ground state is non-degenerate. And closely related, there does not exist any topological charges. There's any local excitation, any excitation of finite energy is actually a local excitation inserted by a local operator. The main reason behind this statement is that if you want to insert a topological charge, the topological charge should be at the end of certain a string operator, and the string operator should be invisible. However, because this mutual gradient statistics is non-degenerate, there does not exist any invisible string operator, and consequently, you don't have any topological charge left. You can also explicitly calculate the specific Hamiltonian on some pre-specified lattice, and you can calculate the ground state degeneracy explicitly and show and conclude that this Hamiltonian does not have any degeneracy. Okay, so I have introduced quantum circuit and one particular Hamiltonian. Now the question is, can you disentangle the ground state of three fermion Walker-Wang model? If this Hamiltonian were degenerate, if it had a topological degeneracy, then I would not ask this question. Well, having a topological degeneracy implies that there does not exist any quantum circuit that disentangles the ground state. It is simply not possible. But this three fermion Walker-Wang model Hamiltonian has non-degenerate ground state. So a priori, there does not exist any obstacle to find a disentangler. If you ask this question specifically for the ground state, one particular state of the many-body system, then maybe this is a fuzzy situation where we do have a very explicit Hamiltonian, and all the other field theoretic arguments suggest that it must be disentangleable, but no one has write down explicit disentangler. However, if you change this question into so that if you remove this constraint, can you disentangle the full spectrum of the Hamiltonian? Then I want to argue that there does not exist any disentangling circuit that disentangles the every eigenstate of the three fermion Walkman model simultaneously. So why is that? Why can't I disentangle this Hamiltonian that has no degeneracy on the ground space? So there are a few things to observe. The first thing is that this Walkman model or Walkman machinery has a special feature that if you introduce a spatial boundary, say at the z equals 0, if you introduce spatial boundary and let the bulk to be my three fermion Walkman model, then it is possible to introduce the boundary Hamiltonians at the spatial surface such that this Hamiltonian hosts annual theory. Remember that this three fermion annual theory is chiral, and everything here, this is a commuting Hamiltonian. And the boundary Hamiltonian can also be chosen to be commuting too. So this is already interesting. The three fermion theory is chiral, and we believe that using commuting Hamiltonians, it is not possible to write down any chiral theory. Nevertheless, by having the bulk, three-dimensional, one-dimensional higher bulk, it is possible to write down Hamiltonian at the boundary using commuting operators, still realizing the three fermion annual theory. That's the first observation. One is that any circuit U blends into identity. What do I mean by blend? Suppose I have a circuit like that. And this is my space. Then nothing prevents me to erase them. So I have a spatial profile of quantum gates such that in the negative z direction, everything is preserved. Here, the action of U by conjugation using this using these gates implements the faithful action as if I had a full circuit. Here, something interesting is happening, but I don't know. Here, nothing is happening. So there exists another, the blending means technically, there exists another circuit, say, well, there, say V, such that in the large negative portion, V matches U. In the middle, something happens. And for very large positive side, V is identity. So in this, if such a V exists, then we say U blends into the identity. And this is the blending region. And since since my circuit consists of strictly local gates, this blending region can have size strict of constant, size of strict. Yeah. Now let's combine these two observations under the assumption, or under the hypothesis that my Hamiltonian, the three fermion Walkman model Hamiltonian, is fully disentangleable. So,
quick question.
Yes.
Do you assume anything about the topology of space, or is it just non-compact?
Oh, there's nothing topological here. I only consider on R3.
Okay. So time is one of the R3 and space is R2.
I'm sorry, I couldn't hear you.
time is R and space is R2. Is that right?
Time is R, oh, space is R3.
Oh, space is R3, and in addition, but there's no boundary in the R3, or is there?
Oh. So space in this case is cross R2. This is my space.
Okay, so it's R plus times R2.
Yeah. Well, to be consistent with my figure, I should have written.
Okay, thank you. Now it's clear.
Yep. So yeah, this is my spatial boundary, and there's the bulk. And suppose I applied the disentangler with the spatial profile that looks like this. I keep all the gates here. I drop all the gates there. Okay, and it has, yeah. Then deep in this side, after applying this circuit, everything is disentangled. So all the extension looks exactly the same as if I had a trivial Hamiltonian. Well, yeah, I or Z, doesn't matter. And at the surface, I didn't do anything. So the original boundary Hamiltonian that described the three fermion theory just survives untouched. In the middle, something interesting happens, but I don't really care. Okay. Since this part is completely disentangled, I can rearrange the Hamiltonian in this half disentangled system to write down a two-dimensional theory. Now my space is now compactified. I'm sorry, yeah. Space is now the relevant space becomes like that. Of course, the constant 100 is nothing but just some convenient large but finite number. So, and the Hamiltonian at the boundary survives, which describes the chiral theory, and commuting Hamiltonian conjugated by any quantum circuit is again commuting Hamiltonian. So we have realized this chiral theory at the boundary at a quasi two-dimensional system. Well, I say quasi, but it's really two-dimensional system. This is just a some small number of qubits, and that's absurd because we believe that the chiral theory is not going to be realizable by any commuting Hamiltonian. But the hypothesis that there existed a quantum circuit that disentangles the full spectrum of the three fermion Wang model implies that we could realize the three fermion theory at the strictly two-dimensional system using commuting Hamiltonians. So the sensible conclusion is that such a quantum circuit does not exist. Now, enter QCA. QCA is a funny nomenclature, stands for quantum cellular automata. I would just call it locality-preserving automorphism, but let's not argue about the naming. I'm just following literature to call it QCA. So the one result is that there exists an alpha, I call it denoted alpha, an automorphism of quasi-local algebra on R3. Well, I should really call it Z3 because my automorphism acts on a lattice, such that alpha acting on, well, conjugating Hamiltonian is equal to trivial Hamiltonian, which is just a sum of single fielded operators. Here, equality is up to rearrangement. Like rearrangement here means that this is one representation of trivial Hamiltonian, but I could easily add another term that would not change any physics, like this, a product of already existing term. It only changes energy of certain excitation, but that's all. The key is that, so I just said that there does not exist any circuit that would disentangle, that would satisfy this inequality. The circuit does not exist, but that does not exclude the possibility of an automorphism. The key is that this alpha does not blend into identity. How we found this alpha is another story, but I would just like you to ask, I would like to ask you to believe me. Explicit calculation note can be found in our paper. It is really complicated. I calculated this alpha using Mathematica discrete, and the Mathematica's output takes about 12 pages long, and it's not instructive at all to show you here, but there exists such an alpha, very explicit. And it's locality preserving, as it's an automorphism of quasi-local algebra. It's a strictly locality preserving. One qubit operator becomes like a 10 by 10 by 10 qubit operator, a finite number. So the conclusion here is then the set of all automorphisms that preserves the locality on some physical space includes, of course, the set of all circuits of small depth, but the inclusion is strict. Previously, this strict inclusion was known, but for a trivial reason. If you consider shift automorphism, the spatial translation cannot be written as a quantum circuit. Argument for that is needed, but I will skip that. But here the strictness is even stranger. We're talking about disentangling a specific Hamiltonian. So even if you throw in circuits and shifts here, still the inclusion is strict. That's one of our main results. Now let me change the gear a little bit to introduce another concept. I will connect this concept to the QCA shortly, and I want to introduce subalgebras. So I imagine I have some lattice. For definiteness, I will only consider finite lattices of some dimension capital D. And there are finite degrees of freedom per lattice point. I'm sure you can generalize this concept to infinite dimensional setting, but let me not do it here. And suppose we have some subalgebra in the trivial algebra. And I say this subalgebra is invertible if the following holds. You give me arbitrary operator inside that algebra, and the condition for invertibility is that it decomposes into sum of products, AJ and BJ, where AJ is an element of A. Oh, I'm sorry. Yeah. O is an arbitrary element in the trivial algebra. Then this arbitrary operator decomposes into sum of products, where one factor belongs to the A, and the other factor, Bj, belongs to the commutant of A. If this holds for arbitrary operator O, then I say this subalgebra is invertible. Now, obviously, the definition is symmetric by undertaking commutants. The A and A prime enters symmetrically in the definition. That's all. Oh, important property. I almost forgot to mention. There's a locality restriction. All of the operator appearing in this sum must be strictly local. So technically, what I demand is that if you collect all the AJs and take the union of the supports and take the diameter of that, then it must be upper bounded by some small constant that is independent of the system size. And similarly, the diameter of union of BJ is upper bounded by the same. So this locality restriction makes it interesting. I mean, if it were not for this locality restriction, this condition is trivial. This is a subalgebra. Whenever the subalgebra is simple, such a decomposition is always possible. But with this locality restriction, things are not that trivial. So why do I care about this invertible subalgebras? The connection is the following. So suppose I have a QCA alpha, and I consider a half space. And I collect all the operators supported on that half space. So the trivial algebra on that half space, and I map it by my given QCA. Simple thought shows that this actually includes a trivial algebra on the quote unquote interior of the half space. So why? Because the interior means that I cut off certain portion here, say minus L, and any operator here has an inverse image within that half space by the locality-preserving property. And since alpha is invertible, I can easily I can easily show that this operator is in the image of the left-hand side. What is left? Of course, what is left is something that I denote by, well, say B, and this something is what I find interesting, and I call it the boundary algebra. Boundary algebra of alpha. You may ask, how does it depend on the position where I cut my space into half, and how does it depend on the direction of the half space and so on? And all of those questions, I do not have a definite answer. For the studies examples, it turns out that B is isotropic. It is independent of how you choose the half space. But I don't see a deep reason why it has to be the case. But anyway, for a given QCA and a given direction and given half space, there is a certain non-trivial factor that I call boundary algebra B. And the theorem is that a subalgebra on D-1 dimensional space is invertible if and only if it is a boundary algebra of some QCA in D dimensions. So this is a more or less complete characterization of the invertible algebras. Invertible algebra, remember, is defined purely in terms of, it has a, well, it depends on the embedding. I mean, it depends on the embedding of A into this trivial algebra, but well, but it does not have any reference to any external thing. But now the theorem says that if you give me such a subalgebra on a D-1 space, then I will find a QCA whose boundary algebra is the given algebra, but the QCA lives in one dimension higher. So
can you say something a little bit about the quantifiers for the parameter L, lowercase L? Like where, like, are you saying that there exists an L such that this and this holds, or I'm having trouble understanding like how L fits into
sure. Yeah, so yeah, since I am talking about finite systems, it's important to put the quantifiers, in the appropriate way. So invertible algebras comes with some specific L.
So in some, that's part of the data for A, right?
Yes, yes,
Okay.
yes. And QCA itself comes with another locality parameter. Given a single site operator under the action of a given automorphism, it becomes some local operator, and the size of that local operator is a data for the given automorphism. And that L has nothing to do with this L. What I demand in the theorem is that for a subalgebra is invertible with some parameter little l. If that's the case, then there is a QCA of range of locality parameter of order L. And conversely, if you give me a QCA of range L, then the boundary algebra is invertible with the locality parameter order L. So I glossed over that locality parameters. But everything becomes very clear if you think about infinite dimensional setting. The L there in the infinite capital L setting, the infinite thermodynamic limits setting, then there all I need is just that there is some locality parameter, and that suffices. So I think, yes, I am on the schedule. So let me just enumerate the results that I am aware, or I have proved, or I have learned from others about this subject, and let's discuss a little bit. The invertible algebras on 0 dimension is always trivial. It's just matrix algebra, and you can show that invertible algebra has to be always simple. So, simple algebra in a finite dimensional setting is matrix algebra again. So this aspect has been observed, although they did not discuss this definition of invertibility. Gross, Nesme, Vogt, and Werner has used this concept of boundary algebra to conclude that any one-dimensional QCA is a quantum circuit plus shift. They have a complete classification in the case of strict locality. A similar statement holds for d equals 1, and that is again trivial. Here, trivial means that there is a quantum circuit that transforms the given invertible algebra A into some matrix algebra over a number of qubits. And this is by Friedman and Hastings. And I proved analogous theorem. Now, with one more quantifier generated by some operator in D-1 is trivial by Clifford circuits. So I consider a smaller class of invertible algebras, and the triviality is again imposed by a finer equivalence relation. But anyway, it is still trivial. And this in particular, these closely related two theorems imply that in D equals 2, every QCA is circuit plus shifts. And if it is mapping a Pauli operator to another Pauli operator, then it is Clifford circuit. So 0 and 1 dimensional setting in the strict locality case is pretty much settled down. Now, the example that I declared to exist, but I didn't show you anything in detail, is that in D equals 2 invertible algebra, maybe non-trivial. Here, the invertible algebra coming from the 3 Fermi and Walker-Wang model is precisely generated by the Annian hopping operators. And this is interesting. We believe that over qubits, and if you give me a Hamiltonian on those qubits on strictly 2-dimensional setting, and if you want to write down a commuting Hamiltonian for 3 Fermi theory, then you are doomed to fail. However, if you allow me to use, if you restrict me to use the operators only in this invertible algebra, then it makes sense to write down a commuting Hamiltonian written in terms of operators in that invertible algebra and realize the 3 Fermion theory. So the operator algebra that you work with is a crucial ingredient when you say, oh, commuting Hamiltonians does not realize chiral theory. Further classification results. Now everything is in terms of Pauli invertible algebras. Here, Pauli means that there exists a generating set consisting of tensor products of Pauli matrices, and I still think, and still we can think about interesting invertible subalgebras. Tensor product of those two, if you give me 2 copies of the same algebra over C2, then it is trivial. More generally, the Weil matrices, invertible algebras generated by Weil matrices, I am referring to this particular one. Powers of it, and the cyclic shifts. If you could write down an algebra in terms of these 2 matrices for some prime p, and still the 2 copies of it is trivial if p is 1 mod 4 prime. Similarly, the same statement, while invertible algebra, if now you have to bring 4 copies. Yeah, if your local degrees of freedom is a prime number mod that is 3 mod 4, then you have to bring 4. And these exponents 4 and 2, they are tight. There are examples that are non-trivial invertible algebras, unless you collect that many copies in dimension O. yeah, these statements are all for all dimensions. And the specific examples comes from d equals 2 case. And one theorem that I'm about to publish is that there are exactly 2 invertible algebra over C2 in d equals 2. Up to, of course, the equivalence relation given by quantum circuits. So yeah, these are the content I wanted to deliver. So let us recap what we have discussed. So the quantum circuits have been used in the study of, well, at least in the conceptual piece in the study of topological phase of matter. And the relation was given by the fact that the ground states along the gapped path of Hamiltonians are related by basically quantum circuits of small depth. And we discussed about the walk-around model associated with the particular anyon theory called the 3 fermion theory, which is chiral. And I posed a question whether one can disentangle the ground state or one can disentangle the Hamiltonian. The ground state disentangleability remains still open, but I have given you a convincing argument that the Hamiltonian as a whole cannot be disentangled by any quantum circuit of small depth. Nonetheless, there exists an automorphism of operator algebra under which the 3 fermion walk-around model Hamiltonian is fully disentangled into the trivial Hamiltonian. And the conclusion from this example is that being an automorphism does not mean that it can be written as a quantum circuit. Now, if you step back and think about automorphism, how the automorphism is discussed in the quantum mechanics, it is usually appears as a one primary family of automorphisms. Here, the one primary refers to the time, but now we have found at least one example of automorphism that is not that does not come from one primary family of automorphisms. It belongs to a different class, and this is the reason I put my title as topological phases of matter of discrete time dynamics. Discrete time dynamics. Automorphism can be considered as a time dynamics generator, discrete, and being not a circuit, I can declare that, oh, there is a distinct, interesting class of, and I put that as a topological phase. And associated with that, I have introduced one object in the operator algebra, and I named it as an invertible subalgebra. And the invertible subalgebra appears as the boundary algebra of any automorphism. And the classification results are being produced, although it is pretty primitive at this stage. The only examples of non-trivial automorphisms or invertible algebra all come from the walk-around model and using different input categories. And there are some triviality results. Yeah, the situation in even higher dimension is widely open. I do not know any non-trivial example, and I do not know any triviality result. So I hope that this topic interests you. Thanks for your interest and attention.
Well, thank you very much, Jeongwan, for an insightful, interesting, and inspiring talk. You had so many results that you talked about, and you often referred to our results. Do you have collaborators on this, or this was modest way of referring to yourself?
So there are a number of papers that are covered in this talk. The very first paper is with Lucas Witkowski and Matt Hastings back in 2018, late 2018. We submitted to a journal, but we haven't got the report yet.
It's very difficult to publish original work.
In the subsequent year, Michael Friedman and Matt Hastings and I have written a couple of papers on this topic. Yeah, there are, I forgot the exact count, but those are my collaborators on this topic.
So I'm sure there are many questions, and also since there are quite a few experts on operator algebra theory, I'd be interested in their perceptions of your talk. But anybody who'd like to jump in, unmute yourself and talk.
If I may, I might start. Can you say something a bit more about why you call this boundary algebra? You have this particular B, and I mean, often boundary algebra has a lot of meaning. I mean, different meanings, unfortunately.
Okay.
So it would be great if you explain, why you named it boundary algebra and where it comes from.
I don't think I named it. It comes from a previous paper, I think. Yeah, I can trace back, but the reason is very naive. I mean, it is associated with the spatial boundary when we consider a certain QCA. So we call it just boundary algebra. No further reason. Maybe, yeah, but if you could if you could tell me what the boundary algebra could mean in various contexts, I will be very grateful.
Oh, in the operator algebra setting, it's often some kind of fixed point algebra.
Okay.
Yeah, so you have, for instance, just to give you an example, you have harmonic functions on a disk, right?
Yeah.
And they are fixed point under Laplacian, where you have a completely positive map, and then the fixed point under a completely positive map, that's a non-commutative. These fixed points are non-commutative boundary in this abstract setting. So I mean, if they leave certain invariants invariant, right, then that's a good indication that your notion of boundary algebra is consistent with other notions of boundary algebra, of which there are unfortunately really many. So I mean, you're free to choose your words, or previous people. It's just that it would be nice if there really is a connection.
Okay. Okay. Yeah, I'll look into those topics. What are the keywords that I can search over?
I mean, yeah, hyperbolic boundary or boundary of operator algebras, Poisson boundary. This is where they use this.
Okay.
Poisson boundary of operator algebras is a very important tool. It's one, I mean, it's not the tool, it's just one important tool, but it's broadly discussed.
Okay. Okay, thank you.
Yeah, I have a question. This is Rad. So this invertible algebras you are talking about, can they be related to the short-term and short-range entanglement? Are they two different notions?
No, I don't think so. Short-range entanglement, well, that's pretty broadly used, somewhat non-technical term, and it only refers to some state that can be mapped to a trivial state by some short depth quantum circuit.
But for those situations, they use the invertible theories.
Right. So my use of invertibility is precisely coincides with those. Here, invertibility, there exists an auxiliary algebra. In this case, the commutant, and if you join them together, then they together generate the trivial algebra.
Okay.
So it makes perfect sense to connect them as invertible states. in the invertible states, what do you mean? You bring some other state and you make them to the trivial state.
Okay. I got it.
So Jeongwan, you had,
Oh,
you
yeah.
looked like you were going to say something.
Yeah. I have two quick questions, more like clarification. So, first, Jeongwan, you have a new paper coming out. So there are exactly two invertible algebras on C2.
Oh,
So I'm guessing one of them is trivial. The other is from the free Fermi Hamiltonian.
yeah,
Okay.
yes.
So what do you need to do to remove the word maybe from your two-dimensional non-trivial QCA? You need to prove something. So what's the maybe? What do you need to do to remove the word maybe?
I think I used the word maybe only for the question whether one can disentangle the three Fermi and Walk-along ground state.
Oh, okay. Maybe I misremember then. So I just want to understand the statement clearly. So are you, well, the thing is mathematically, do you have a proof that the full Hamiltonian cannot be made trivial, and you're maybe not sure about the ground state? If that's what you are saying?
No. So speaking of the non-triviality, we do not have a full proof that it is non-trivial.
Okay.
We have reduced the problem into the statement that using commuting Hamiltonians, you cannot realize chiral theory.
Okay, in two dimensions.
In two dimensions.
Okay, thanks. Yeah.
So Nat, do you have a question? Please turn on your video.
Hello. Hi, Jeongwan.
Hi.
I was wondering
Can you
for
turn on your
result.
video, please, so we can see
Yes,
you?
sorry, just a second. Can you see me? Hi. I was wondering for your Pauli, sorry, for your results about the QCA, was that only for Pauli's invertible algebras, or
Was there
was it that you said there are exactly two invertible algebras?
Only for Pauli.
Pauli?
Yeah, only for Pauli.
So there's
Only for
possible
Pauli
that
over
there are
qubit.
more.
Yeah, there could be more.
I see.
So, Juven, you have a comment?
Yes, I have a question. Sorry, I'm using a device that the camera doesn't work, but if it's okay, I will just go ahead to ask. So the question is that it seems time evolution probably works for quantum Hamiltonian, not necessary gap or topological. So I wonder whether there's a reason or mostly discussions for topological gap phase.
No, it was just happened to be our route to arrive at this object.
And whether there are some comments you can make for a more general Hamiltonian system which are not gapped or topological.
Not in a meaningful way. I mean, most of the properties do not really change if you apply this automorphism to a topological theory. Only interesting, is when you apply this to a, something that looks like a topological, but you don't have a topological degeneracy, like a walk-along model. For other Hamiltonian systems, if you apply this automorphism, well, that's pretty wild. I have no useful comment.
Okay. So there is not quite a concrete lesson we can take for general quantum circuits, not the gapped one. Do you know? I think you think also apply.
Yeah, I'm not sure what to say. Well, so I can remark one advertisement that we have applied this QCA knowledge and technology to the study of a certain SBT state in 4+1 dimensions by endowing the three-dimensional submanifolds in that 4 space with this QCA on average, and let them fluctuate. And that way, we obtained some state that sits in the beyond cohomology classification. But that again is not a application of QCA into dynamics. It's again an application to study some static property.
All right, thank you very much.
So are there other comments or questions?
Yeah, just a small, maybe understanding the definitions questions. When you say shifts in 2D, are you just referring to translations?
Yes.
So
no. It's slightly more general than that. It's locality-preserving permutations.
Okay, so I can imagine like in a 2D grid, like some of the things are moving around, clockwise or something like that.
Yes. But I want to remark that this my definition of QCA excludes spatial rotation, for example, because the spatial rotation means that there's some center of points where the things are rotating about, and the far away things move too far, and we're not considering that.
Right. So what about something like this, where you're not exactly rotating through a fixed angle, but you kind of like move things around in a circular fashion? This seems like a QCA, but it doesn't seem like. But it doesn't seem either like it's a combination of circuits plus shifts either in your definition, right?
In my definition of shifts, that shifts includes your example.
Okay, I see. Thank you.
Are there other comments? Questions? We have quite a few experts here. Well, if there's no other comment, I want to thank Jeongwan again for a really interesting talk. And we'll look forward to the papers coming out, and also in your slides to have the references to the papers. So thank you again, and see you next week with Francis Brown. Bye-bye.
Thanks, Brent. Bye.